On the left side of your screen, there is a disc of diameter 600 mm. And on the right side of a screen, there is a cylinder of diameter 200 mm. And both have equal mass, 20 kg. Now imagine these shapes are mounted on set of bearings and connected to electrical motors, and try to rotate these shapes around their central axis. So could you tell me, if these both shapes need to rotate at the same speed, let's say 100 rpm, then which motor would require more torque? Would the required torque need to be same since both have same mass and same speed? Or would the motor for disc need to be more torque than the one for cylinder? What do you think? Which one would require the greater torque? How we can calculate the required torque for motors? Well, as we know, the torque is the product of force F and the distance R. For example, if we applying a tangential force of 5 Newton at a lever that is 2 meter long, the torque required to turn around the pivot point would be 5 Newton into 2 meter, 10 Newton meter. But this case is different. We are not applying a force at circumference or at a distance from the axis. Here the motor is directly applying a turning force to the center of the disc or cylinder. There is no lever, there is no R, and no tangential force. The torque is applying directly to the central axis. So how we do calculate the torque, required torque for these motors? Moreover, this is not a surprising or unique case. As a mechanical design engineer, we encounter such cases very often. We often design indexing table for assembly line, where we rotate a disc plate around their axis very precisely. Also, conveyor rollers, where a cylindrical rollers rotate around their central axis. Also in ball screw or lead screw, we rotate the ball screw around their axis. And in all these cases, we must calculate the required torque to sizing the motor correctly. However, if your physics is still good, then you must be familiar with a term, moment of inertia. And probably you know the answer to this question as well, that the disc has a larger diameter. That means the mass is distributed further from the axis. So its moment of inertia is higher as compared to cylinder. In fact, the disc has moment of inertia of 0.9 kg meter square, while the cylinder has a much lower moment of inertia of 0.1 kg meter square. So does this means the motor for the disc will always require more torque? Not necessary. The torque required to rotate an object doesn't depend solely on its moment of inertia. It also depends on angular acceleration. That is how quickly we need the object to reach its target speed. If you are okay with a slower start, then required torque would be lower. But if you need a quick start and stop, like an induction table, then the torque requirement increases significantly. So to choose the right motor for any rotary application like indexing table or conveyor, we need to master two things. One is what does actually means of moment of inertia, how to calculate it and how to optimize it for a rotary mechanism. And the second is how to estimate the acceleration time for particular rotary mechanism, which again depends on two things. One is application itself. For example, application like indexing table, quick start and stop are critical. But for conveyors, blowers, fans, acceleration can be slower. And the second is type of motor. For example, servo motor can take much more time to accelerate, whereas for an induction motor, too long a startup time can be lead to stalling or overheating. So hi there, this is Ayush from Master Mechanical Design, and today we are going to master the motor sizing for rotary applications. We will go through the two examples, one for induction motor sizing for a belt conveyor and another is servo motor sizing for indexing application. And by the end of this video, you will have a clear understanding of how to sizing the motor for almost any rotating application. But this is just an outcome of this video. The main thing, the core thing we are going to master is inertia and moment of inertia. Not just physics behind this, but we will also understand what moment of inertia really is, how it works, and why it's so important in machine design. I will show you where we use torque equal to F into R and where we use torque equal to I into alpha. So after watching this video, the motor sizing won't intimidate you anymore, and you will become a master of motor sizing for almost all the application. Before we start, let me quickly mention our today video sponsor. Our sponsor today is JLCMC, a marketplace that makes it easier for engineers, manufacturers, and hobbyists to find the quality mechatronics part for their projects. JLCMC offer a wide range of components all in one place. So whether you are building a robot or machine or just need some specific to your project, you can find almost all the parts you need at one spot with industry standard quality and all at competitive price. JLCMC also ships globally, so no matter where you are, you can get the part. And also you can download the CAD models of most of components directly from their website. And here is a special offer. If you register on their website, you will get a $19 USD for your first purchase. Plus, with Black Friday coming up, they have an awesome deal. A screw set with 1750 pieces just for $5. It's include M3 to M6 hex screw. So check the link in video description below. And big thanks to JLCMC for supporting the channel. So what is inertia and moment of inertia? So first off, the inertia is related to linear motion, the motion in a straight line. And moment of inertia, or we can say mass moment of inertia, or second moment of mass, or most accurately rotational inertia, is related to rotational motion. But before understanding moment of inertia, let's start with inertia. So you have probably heard this word many times back in school, high school, in college, and even in job. But what does it actually means? Is inertia a force or is it mass? Well, inertia is neither a force nor just mass. It is actually a property of mass, a natural tendency of mass of an object to keep doing what they are already doing. If something is at rest, it will naturally want to be at rest. If something is moving, it's naturally want to be keep moving in the same direction at same speed. In simple terms, inertia is a resistance to change in its motion in their current state. And Isaac Newton refine and codify the same concept of inertia in the first law of motion, also known as principle of inertia, that every body preserve in the state of rest or uniform motion in right line unless it's compelled to change the state by the force impressed thereon. What this simply means is a body in its rest means the velocity and acceleration is zero. The natural tendency of the body to be at rest cannot automatically go into motion. And if an object is in uniform motion on a straight line, uniform motion means constant velocity. Velocity can be anything but must be constant, which again means zero acceleration. Then the object will remain in uniform motion on a straight line. But unfortunately, we cannot experience this on Earth's surface because of gravity, friction, and air resistance. But you must have seen in videos When an astronaut float around an object, the object continued to move at constant velocity because in a space where there is no gravity and air resistance. So once the object gets accelerate, it will remains in uniform motion unless we apply a force on it. So here is a big question. How much force is needed to change the motion? How much force is needed to change the state? Means if something is at rest, then how much force would take it to get in moving? Or if something is already moving in a straight line, then how much force would require to change its speed or its direction? So let's understand it step by step. So first, if you just want to start the motion, regardless of how fast and slow, then any amount of unbalanced force can do the job. Even a tiny push will work. For example, in deep space, far from the gravity and air resistance, any object, no matter how heavy, will start the moving if you apply any force at all, even something as small as 0.001 Newton. And once it starts moving, it will keep moving in the same direction forever. That's the Newton's first law. A body at rest stays at rest, and a body in motion keep moving in motion in a straight line unless acted by an unbalanced force. Even on the Earth's surface, any amount of unbalanced force can start the motion. But here is a catch. You also need to overcome the frictional resistance. If the applied force is less or equal to the resistance force, nothing will happen and the object will not start moving. But applying even a little extra force than the frictional force, the object will start moving. But if you want to achieve a specific velocity in a specific time, then the required torque would depends on two things. The first is mass of object and second is how quickly you want to accelerate it. Newton's second law of motion. Force equal to mass multiply acceleration, F equal to ma. Confusing, isn't it? So let's understand these both things with an example. Imagine we have 20 kg fixture mounted on a slider and the slider has a coefficient of friction 0.5 and we want to use a pneumatic cylinder to slide this fixture. So how do we calculate the required force to move it? So first we need to calculate the force need to overcome the friction. The frictional force equal to mu mg, and for our case the frictional force would be 98.1 Newton. Now if pneumatic cylinder applies exactly 98.1 Newton or less than 98.1 Newton, the fixture won't move because the frictional force and the applied force cancel each other out. So to move the fixture, we need to apply an unbalanced force. For example, if we apply 100 Newton, which is just 1.9 Newton more than the frictional force, the fixture will move. But here is the interesting physics. The amount of this unbalanced force determines how quickly fixture will move. For example, let's say the slider length is 1 meter and you want the fixture to cover this distance in just 2 seconds. So the fixture initial velocity is 0 meter per second because our fixture is at rest and the distance is 1 meter and the time is 2 seconds. So to calculate the required acceleration, we can use the linear motion equation S equal to ut plus half at square. Put the values. So acceleration is 0.5 meter per second square. And now we can use Newton's second law formula, F equal to ma. The mass of fixture is 20 kg and the acceleration is 0.5 meter per second square. So F equal to 10 Newton. So this is an unbalanced force required to achieve the desired acceleration of 0.5 meter per second square so that fixture could cover 1 meter within 2 seconds. And remember, in this calculation, there is no friction, no gravity. It's purely based on the mass and acceleration. The greater the mass or the faster you want to accelerate, the more force you will need. So the total force required to move this fixture equal to the force to overcome the friction, 98.1 Newton, plus the unbalanced force to achieve the desired acceleration, 10 Newton. So in total, we will need 108.1 Newton to move this fixture 1 meter in 2 seconds. Now, whether the pneumatic cylinder can actually provide this force quickly enough, that depends on other factors like airflow rate, but that's the different problem. So in summary, the inertia is a resistance to change in motion, and it depends on the mass of the object. Greater the mass, greater the inertia. And the required force to change in inertial state, rest to motion or motion to rest, depends on how quickly you want to accelerate the mass. Now, what about moment of inertia, the rotational inertia? So, as the inertial mass is related to linear motion, moment of inertia is related to rotational motion. When an object rotates around their own internal axis, like spinning of something like this rod, it's rotated around their own axis, internal axis. Axis can be in this way also. It's also an internal axis within the body. So this rotation has also moment of inertia. But the moment of inertia around this axis is more as compared to this axis, which we will understand later. Also, the axis doesn't have to be necessarily fixed. The axis can move itself when the object is rotating like this. Also, if you are rotating something only to a specific angle, there will be also moment of inertia. And the moment of inertia plays the same role in rotational motion as mass does in linear motion. Just like mass resists the change in linear motion, moment of inertia resists the change in rotational motion. But here is the key difference. The moment of inertia doesn't just depends on amount of mass. It also depends on how the mass is distributed, related to the axis of rotation. If the mass is further from the axis, the moment of inertia would be higher, means will more resistance the change in rotation. And if the same amount of mass is somehow closer to the axis of rotation, then moment of inertia would be lower, means will resist less to change in rotation. Now, in linear motion, if we want to change the inertial state of a point mass, we apply a force in the direction we want the motion to occur in a straight line. And the equation we use is F equal to ma. But what if we connect this point mass to a pivot point with a zero mass rigid connection? And if we want to rotate this mass around this pivot point in the same plane, then how much torque will need to apply around the pivot point? Well, we know the relation between force and torque. Torque equal to force into radius r. Now, what's force? Force will still ma, right? But in this case, as we are rotating, we need to replace the linear acceleration with angular acceleration. And we also know the linear acceleration equal to r angular acceleration alpha. If you forget, linear velocity equal to r angular velocity. Linear displacement equal to r angular displacement. So the torque T equal to m r alpha into r, which simplified to m r square alpha. Now, if we compare this torque equation to the linear equation F equal to ma, so for mass we have torque, for linear acceleration we have angular acceleration, and for mass we have mr square. This mr square is actually moment of inertia. It's denoted as I in most classical physics equation, but in engineering we often use J to represent the moment of inertia. But this is exactly the same, the rotational inertia, moment of inertia. So this was all about the moment of inertia and their relation with torque. Torque equal to I, moment of inertia, into alpha, angular acceleration. The more moment of inertia an object has, the more torque will require to accelerate it. And the faster you want to rotate it, the more torque will require. If you are wondering if I equal to mr square, then why different shapes have different moment of inertia formula? Why not just mr square? So let me break down this a bit. So first up, the moment of inertia is an extensive property, or additive property. So if there is two mass instead of one, then the moment of inertia will simple to 2mr square. If there is one more other mass at half of the radius, then it will become mr square plus mr divided by 2 square. Now if suppose this is a rigid body like a disk or cylinder, then there is an infinite mass, infinite point mass. So instead of adding them, we integrate to find the total moment of inertia. And here I don't want to dive into math of integration, but the point I want you to understand is the I equal to mr square represents the moment of inertia of a point mass at a distance r from the rotational axis. But in real world, we often work with rigid bodies like cylinder, disk, or any other shape. So to find the moment of inertia of these shapes, we perform integrations and the results depends on the shape of the object and the position of the axis of rotation. So I will leave these formula in video description for your reference. So this was all about the theory of moment of inertia. And now let's understand how these theories applies in motor sizing calculation. So we will do the two calculation. Calculation of an induction motor sizing for belt conveyor and the servo motor sizing for indexing table. So let's first understand the calculation of an induction motor for a belt conveyor. And then we will understand the sizing of servo motor for indexing table. So let's say we have a 3 meter long belt conveyor with roller of 200 mm diameter, and the load of our belt is 80 kg and the mass of the belt itself is 20 kg. Now, what would be the required torque of motor to drive this belt conveyor? So we need to calculate the required torque for two components. One is pulling force required to overcome the friction between the belt and the belt support, and second is required torque to overcome the moment of inertia of the whole system. So first let's calculate the pulling force. So the total load is 80 kg of material plus 20 kg of belt, so 100 kg in total. Now let's assume a solid support below the belt, and the coefficient of friction between the belt and support is, let's take it as 0.2. So the required pulling force would be equal to frictional resistance, which is mu mg. Put the values 196.2 Newton. So what now? So think of this pulling force as attached to the roller with a string. So when roller will rotate, this pull will act like a tangential force, something like this. So to find the required torque, we need to multiply this pulling force by the radius of driving roller. So the roller has a 200 mm diameter, so the radius would be 100 mm, 0.1 meter. So the required torque would be 19.62 Newton meter. But we are not done yet. We also need to calculate the required torque to accelerate the whole system from rest to motion. And this depends on moment of inertia of the system, the torque equal to moment of inertia into angular acceleration. So let's first calculate the moment of inertia. So the total moment of inertia includes the moment of inertia of rollers and moment of inertia of load over conveyor, including the conveyor belt. Yes, the load and the belt is also at the rest, so we need the torque to accelerate them too. So for rollers, the moment of inertia around their rotational axis would be half mr square. So moment of inertia of each roller would be 0.075 kg meter square. So for both roller, it's 0.15 kg meter square. Now for the load and the belt, the total moving load is 100 kg, but it's moved linearly. So most of us doesn't consider this as a moment of inertia, but we have to. So we will have to convert this in an equivalent moment of inertia. So imagine this load as a single point mass at the roller's circumference, because the belt and the load has to be pulled over the belt circumference. So the moment of inertia of a point mass at distance r is equal to mr square. So for 100 kg at 0.1 meter radius, it would be 1 kg meter square. So the total moment of inertia equal to 0.15 plus 1.15 kg meter square. And now we comes to the tricky part, deciding the acceleration for motor. More acceleration means more torque would be required, and if we could start slowly, the less torque would be required. So to decide the acceleration, first we need to understand that how an induction motors actually works. So mostly we use a synchronous induction motor. Means there is always a slightly difference or slip between the rotational speed of the electromagnetic field in stator and the rotor of the motor. Under no load condition, this slip is typically about 1%. However, when we apply a load, the slip increases. For a standard motor, this slip should not be exceed 5%, as the higher slip can cause overheating and reduce the motor lifespan. Some special design motor allow slip up to 8%, but for most of standard motors, staying between 1% to 5% range is crucial. Now let's consider a 4-pole induction motor operating at 50 Hz for this conveyor. So the synchronous speed of 4-pole motor would be 1500 RPM. I have already explained synchronous speed of motor in this video. For 2-pole, speed would be 3000 RPM. For 4-pole, speed would be 1500 RPM. So if we want an optimum motor sizing, we can consider a slip of 5% at full load. So the speed of motor at full load would be 1500 minus 5% of 1500, 1425 RPM. So we have the final speed of motor at full load, and we have also initial speed 0 RPM. Yes, we're sizing the motor to start the system from the rest. Now, when we will start this induction motor, it will begin at 0 RPM, which means the slip will be initially 100%. And as the motor accelerates, the slip will gradually reduce to around 5% under the full load operating condition. So during this starting phase, the motor draws a very high current, 5 to 7 times more than the normal operating speed. So if this starting time lasts too long, the motor can overheat and potentially burn out. So to avoid this, the starting time of induction motor must be controlled based on the method we use. For direct online DOL starting, the acceleration time should be between 1 to 5 seconds. For star delta starting, it should be range from 3 to 10 seconds. With a soft starter, it can extend to 15 seconds, and using a VFD, the starting time can be programmed to as long as 30 seconds. So for optimal motor performance, our goal should be to achieve an acceleration time of around 5 seconds. So we have the acceleration time, 5 seconds. So now we can calculate the acceleration of the motor. But first we need to convert the final speed 1425 RPM to the radian per second. So 1 RPM equal to 0.0467 radian per second. So 1425 RPM, 149.15 radian per second. If you are wondering how the 1 RPM equal to 10467 radian per second, so 1 RPM means in 1 minute in 60 seconds, 1 full revolution, 360 degree means 2 pi radian. So in 1 second, 2 pi divided by 60, 0.10467 radian per second. Very simple. So the angular acceleration omega divided by t equal to 29.83 radian per second square. Now put these values in the torque equation. It would be 34.30 Newton meter. So the total required torque to run this conveyor with full load equal to 53.92 Newton meter. This means the motor should provide 53.92 Newton meter or more. But if you are using a gearbox, let's say 1:10 ratio, then the motor required torque would be reduced to just 5.3 Newton meter. So I hope you understood that how important is to calculate the moment of inertia and choosing the right acceleration for motor sizing. Now let's understand the servo motor sizing for an indexing table. So let's consider an indexing application. An index round plate of 1 meter diameter, mass 100 kg. And having two fixtures and each mass is 20 kg. The plate is supported by a cross roller bearing, so the outer diameter of the bearing is 200 mm. And the cycle time to rotate this plate from one station to another by 180 degree is 2 seconds. And we have to use a servo motor to index this whole system. So how much torque does servo motor need to perform this task? Interesting, right? So the total required torque of the servo motor need to be sum of two parts. The first is frictional torque to overcome the resistance in bearing. And the second is acceleration torque to get the moment of inertia of system to accelerate. So let's tackle the frictional torque first. So let's assume the coefficient of friction of the bearing is 0.05. This is ideal for bearings. And the total mass of the system is 100 kg, mass of the plate plus 40 kg, mass of the both fixture, 140 kg. So the frictional force F equal to mu mg, 68.67 Newton. And the radius of bearing is 0.1 meter, half of 200 millimeter. So the frictional torque to overcome the resistance would be torque equal to F into R, 68.67 into 0.1, 6.867 Newton meter. So the torque needed to overcome the friction is 6.867 Newton meter. Next, we have to calculate the torque required to accelerate this whole system. The torque equal to moment of inertia into angular acceleration. So the moment of inertia of this whole system would be moment of inertia of plate half mr square, 12.5 kg meter square, plus the moment of inertia of each fixture, 5 kg meter square. So the total moment of inertia of system would be 22.5 kg meter square. Now in this equation, we need to calculate angular acceleration. But how? So here we have to understand a very important thing, that motion doesn't start at full speed. It's always begin at zero velocity, increase to the desired speed, and then deaccelerate. You cannot instantly jump to any desired speed in 0 seconds. There is always a sometimes to accelerate and to decelerate, even for a fraction of second. So now in this case, we got 2 seconds to make this whole thing happen. So we can divide this time into like 0.5 second for acceleration, 0.5 second for deceleration, and 1 second for uniform motion in between. But if you want more smooth start and stop, we can go for 0.75 second for acceleration and deceleration and 0.5 second for uniform motion in between. Actually, this division is up to you, up to the programmer. And the thing is, you just have to give the more time, or we can say enough time, for acceleration and deceleration as much as possible. I hope you got it. So we have the total angular displacement 180 degree by radian. So we can use the angular displacement equation for each stage. Angular displacement equal to half initial angular velocity plus final angular velocity into time. So for angular displacement at acceleration, since the initial angular velocity is 0, angular displacement at acceleration equal to half omega max t, 0.75. Same for the deceleration. And for uniform motion, omega max is constant, means initial velocity and final velocity is equal. So angular displacement at constant velocity will be omega max into time, 0.5. And we can sum up this all. So pi equal to 1.25 omega max. So maximum angular velocity omega max equal to 2.51 radian per second. So the angular velocity at the end of the acceleration phase is 2.51 radian per second. So the angular acceleration alpha can be calculated as angular max 2.51 divided by time taken, 0.75. For acceleration, 3.35 radian per second square. So the needed torque to accelerate and decelerate this whole indexing system would be the moment of inertia of whole system 22.5 kg meter square into angular acceleration 3.35 radian per second square, 75.37 Newton meter. And the total torque 6.86, the frictional resistance torque, plus 75.37, 82.23 Newton meter. So this is how we sizing an servo motor, and this is quite different from sizing of an induction motor. With servo motor, we do not really have to worry about the acceleration time in same way. The reason is simple. The servo motor working principle is different than an induction motor. The servo motor is designed for the precise control. However, it doesn't mean that we can just decrease the acceleration as much we want to rotate any heavy system with large moment of inertia. There is actually a limitation when it comes to that how much moment of inertia a servo motor can handle. And we can find this limitation in servo motor catalog from the manufacturer. Let me give you an example. For a 400 watt servo motor, the catalog specified the allowable moment of inertia 10 times of motor moment of inertia. And here the motor's moment of inertia is 0.09 into 10 upon minus 4 kg meter square. So the allowable moment of inertia for this motor would be 10 times that value, which equal to 0.409 into 10 upon minus 3 kg meter square. So once we calculated the required torque for the system, don't just select the motor only based on torque and rated speed of servo motor. We will also need to verify the allowable moment of inertia for the motor and make sure the selected motor moment of inertia should be greater than the system moment of inertia, or else the motor wouldn't work properly. So this is it for this video. I hope this will help you in sizing of motor for almost any rotary application. And new fresh machine design series are coming very soon. So please stay tuned, and thank you so much for watching, and I will see you in my next one.